Okay, this lesson is for section 2.4. We're going to be looking at polynomial inequalities. So we're going to be doing similar to what we did yesterday with just inequalities, but now we're going to be doing it with rational expressions and higher polynomials, higher degree polynomials. So the first example here, if we were to have a graphical representation of what the inequality looked like. So for example, in numbers 1 and 2, pretty basic quadratic here. I'm looking at a picture of this quadratic graph, and I want to know when it's less than 0. So in this picture here, it's clearly showing that your polynomial is going to be less than 0 from this root to this root. So and it looks like in the graph from -1 to 3. On the open interval from -1 to 3, this polynomial will be less than 0. Okay, and it's again less than 0, so we don't have a closed bracket here. Now on the other hand, this polynomial will be greater than or equal to 0 from all numbers from -infinity up until we get to 1. So if we wanted to write this as greater than or equal to 0, because we can't equal 0, right, at -1 here, sorry, -1. At -1 it actually equals 0. We would write this as -infinity all the way up to -1, closed bracket here. And the union of this with from 3, with a closed bracket, 3 all the way to, because this is going to increase forever, to positive infinity. And that should be a parenthesis. Okay? So let's say we don't actually have a graph. We don't have a picture. We don't know what it looks like. Well, what we're going to look for are things called key numbers. Okay, key numbers are the roots of your polynomial and other restrictions on your domain. So right here we don't have any other restrictions on our domain, but we can find roots. This is the same inequality that we were just looking at. So x squared minus 2x minus 3 is less than 0. You always want to make sure that you have your inequality less than 0. Okay. So if I were to factor this, I have x minus 3 and x plus 1 is less than 0. So I get key numbers here at x equals 3 and x equals -1. These are my two key numbers. These are the roots of that polynomial. These are going to be called the key numbers. What that's going to do is separate a number line. So you're going to just always graph a number line to figure out where you're having special things occur in your polynomial. Like we already know what this quadratic looks like because we had a graph, but we're not going to know what it looks like every time. So I just want to use that same example so you get an idea of what to do when you don't have a graph. So we know that there's something special that happened at -1 and at 3. So this actually breaks up your number line here, your x-axis, into 3 distinct parts. You have one interval from -infinity up into -1. You have another interval from -1 to 3. And you have a third interval from 3 to positive infinity. Okay, now what you're going to do is test all of the cases of what happens in your polynomial, your factored polynomial here, when you plug in a number that's falling into this region, and this region. So you have 3 different test regions that you're going to try out. So let's, for example, take from -infinity to -1. So what I'm going to do is think of a number that falls within this region. Let's try -2. If I plug -2 back into this inequality, this first part, x minus 3, this stays negative, right? If I plug in -2, that stays negative. If I plug in -2 into x plus 1, this is also going to give me a negative value. So resulting in a negative multiplied by a negative, this turns into a positive, and this is obviously not less than 0, but I'm going to put underneath in this interval that this is a positive value. So anytime I plug something in within this value here, I get a positive answer for my polynomial. Now when I test the region between -1 and 3, I'm going to do the same thing. So let's test between -1 and 3. I'm going to select a number between that. Let's just say we use the number 0. Okay, so if we use the number 0, I'm going to test again within x minus 3 and x plus 1. X minus 3 becomes negative, right? This is a negative value, and x plus 1 is positive. This results always in a negative. When I multiply this negative times a positive, I will always get a negative if I pick any number within that interval. So back on my number line, I'm going to put a negative here. Now the last one to test is from 3 to 0. From 3 to 0, let's pick, or sorry, 3 to infinity, not 3 to 0, that doesn't make any sense. From 3 to infinity, I can pick any number. We can pick the number 4. Let's try 4. If I test it within x minus 3 and x plus 1, this answer, no matter what, this part will always be a positive. And if I plug in any number that's greater than 3, it will also always be positive. So resulting in, when I multiply those two together, a positive result for that polynomial. So I'm going to put a positive sign here. Now, without a graph, we can tell that between -1 and 3, this polynomial is going to be less than 0. And that's what we were looking for earlier, right, in this top number 1 here. We were looking for the interval in which it was less than 0. Well, we just found it, right, between -1 and 3. If I had flipped this sign and asked you for greater than 3 or greater than 0, then of course you would pick this interval joined with this interval, which is what we did in problem number 2. So that's just a really basic one. Now in the next example, number 4, we want to do the same approach. We don't know what this looks like, so we're going to test regions. Okay, so give me a second to erase and set this up for you guys. Okay, so I'm going to need a lot of room. You're probably going to need a lot of room on your paper too, so there is some room here, I think, to be able to write all the work that we're going to show. So our goal here when we're solving a polynomial inequality is we want to get 0 on one side and we want to find the key numbers. So those, again, key numbers are restrictions on your domain or roots of your polynomial, okay? So in this case, there's no restrictions on our domain, but we can find some roots here. So let's subtract over 14x cubed and add over the 48x squared so that we can get 0 on one side. Now what I'm going to do is try to factor this. So I'm going to pull out a GCF of x squared. I have x squared minus 14x plus 48. That's less than or equal to 0. Okay, at this point now what I'm going to do is try to factor even further. If I can't factor, then I would use the quadratic formula. Okay, so this is factorable, so I'm going to get x minus 6 and x minus 8, here for that quadratic in the inside, is less than or equal to 0. Okay, so from here we have 3 key numbers. Our key numbers are x equals 0, x equaling 6, and x equaling 8. So what I'm going to do, and this you always have to do this in order to see where your intervals are at, I'm going to create a number line and I'm going to place 0, 6, and 8 on that number line. And then it's actually breaking it up this time into 4 different regions, right? We have 4 different intervals here that these key numbers break our number line up into. So I'm going to label these. This is from -infinity up to 0. This is from 0 to 6, 6 to 8, and 8 to positive infinity. Alright, now I'm going to test each case. So let's begin by testing -infinity to 0. Remember, you're going to pick a number between -infinity and 0, so let's try -1. If you need to have a concrete number, then plug in -1 and show the work for it. Otherwise, what I do is I just say, okay, if this number is negative, what happens to the polynomial? So, alright, if I plugged in -1 into my factored expression here, I get a positive. X squared here is going to become positive. If I plug in a negative number, like -1, into this second inequality here, x minus 6, I get a negative. I result in a negative number here. And if I plug in again another negative into x minus 8, I plug -1 into here, right? -1 minus 8 is -9, so I get another negative. Overall, this polynomial then is going to be positive because I have 2 negatives here making a positive multiplied by another positive. So overall, this is going to be positive. So on this number line here, I'm going to write in that this is a positive interval. From -infinity to 0 is a positive interval. Now let's test our next interval from 0 to 6. So from 0 to 6, we're going to test, I'm just going to write this out each time. Test a number between 0 and 6. Let's try +1. Well, if I put in +1 into here, I get a positive. Plug in +1 into here, I get a negative. Plug in +1 here, I get a negative, resulting in, overall, a positive. Okay, our next interval from 6 to 8. Plug in a number between those, in that interval here, let's plug in 7. X squared is going to give me a positive. x minus 6 here will give me another positive, and x minus 8, if I plug in 7, will give me a negative number, which is resulting now in a negative. So from in the interval 6 to 8, we result in negative numbers for our polynomial. Now when we test 8 to infinity, let's try 9. X squared is going to become positive, x minus 6 is positive, and x minus 8 is also positive, resulting in a positive. Okay, now let's go back to our original inequality, and that was here, once I rewrote it. We want to know when this polynomial is less than or equal to 0. Okay, so at the point, we know that in the interval from 6 to 8, it's less than or equal to 0. What we don't know, though, is whether or not we should have open or closed brackets. Now, because this is equal to 0, remember that at x equals 6, this whole term drops to 0. If x equals 8, this whole term drops to 0. So this is going to be a closed interval from 6 to 8. This polynomial is less than or equal to 0. Okay, so we also need to consider the fact that when x is 0, right, at the point x equals 0, the whole polynomial also equals 0. So in this case, it's only going to be the union of just one number in the set, just 0. So this is showing from any real number between the interval 6 to 8, it's closed, with the union of the one element when x is 0, then our whole polynomial here is equal or less than or equal to 0. So this here would be my final answer, showing all cases in which this polynomial is less than or equal to 0. Okay, so you guys can go ahead and pause and try this next example, and of course play it back if you don't get the exact answer from the key. I'm going to go through the solution in its entirety, otherwise you can skip ahead if you do get this correct. Alright, so I'm going to get to factor this right away. So I'm going to pull out the x here, and I have x squared minus 2x minus 3 is greater than 0. So I can factor this into x minus 3 and x plus 1 is greater than 0. Alright, now my key numbers here are going to be x equals 0, x equals 3, and negative 1. So on a number line, I'm going to go ahead and draw out those 3 points. So I have negative 1 first, then 0, then 3. So make sure you're just drawing it in correctly, because I've done that before where I put 0, negative 1, and then 3. Like, I'll do it in the order that I solved, and then it won't make sense because I'm trying to write an interval that doesn't make any sense. So make sure you don't make that mistake like I do. Okay, so this interval here, it's splitting this up into 4 parts again. We have from negative infinity to negative 1, from negative 1 to 0, from 0 to 3, and from 3 to positive infinity. Alright, so what we're going to do is test this factored expression, x times x minus 3 times x plus 1. I'm just going to leave it one time. I'm just going to clean up a little bit of the work here that I've been kind of all over the place with my work, but I'm just going to test it in here, so just refer back up to here when you see where I'm testing the regions. So let's first start with negative infinity to negative 1. I'm going to pick a number, let's say negative 2, and I'm going to plug it in. So if I plug this in, I still get a negative. I plug it in here, I get a negative again. Plug it in here, and I get a negative again. So overall, I have a negative here. So from this interval, from negative infinity to negative 1, we result in the negative. Alright, so from the interval negative 1 to 0, and let's pick a number in between there. Let's actually let it equal, I guess, negative half. Okay, so plug in negative 1/2 here. This is still going to be negative. Negative 1/2 here will still be negative, and negative 1/2 plus 1 will result in a positive. So here I get a positive number in the polynomial. So I'm going to go back to here and label that. Now let's test from 0 to 3. So from 0 to 3, let's pick the number 1. I get a positive if I plug in x equals 1. I get a negative here, and I get another positive here, resulting in a negative. So this interval here is negative. From 3 to positive infinity, let's plug in 4. If I plug in 4, I get a positive. If I plug in 4 here, I still get a positive. If I plug in 4 plus 1 here, I get another positive number, and I result in, overall, a positive number. Okay, so our goal here to answer this beginning inequality was to find out when it's greater than 0. So at these two intervals here, the polynomial x cubed minus 2x squared minus 3x is greater than 0 because these are positive, right? These are the only two intervals where it's positive. So my final answer here is going to include from -1 to 0 with the union of 3 to infinity. These are the values for which it is greater than 0. So I don't have any closed brackets here because I'm not interested in knowing where it's equal to 0. I just want to know when it's actually positive. Okay? Okay, number 5 is our first rational expression inequality. What's nice about this one, it's already factored for us, so right away I have key numbers here. And remember, key numbers are restrictions on your domain as well as roots. So in this inequality here, if I set it equal to 0, then I get a root at x equals -2. But I also have a restriction in the domain, x cannot equal 4 either, right? So these are my key numbers here at -2 and 4. So I'm going to split up my number line. It's going to create 3 distinct intervals, so from -infinity to -2, from -2 to 4, and from 4 to infinity. I'm going to test this inequality. So x plus 2 over x minus 4. I'm going to test this rational expression. Okay, so let's do -infinity to -2. So from this interval here, let's pick a number. Let's say it's -3. If we plug it in, the top is going to be negative. The denominator is going to also be negative, resulting in a positive number. If I test from -2 to 4, let's pick the number 0. The numerator here is going to be positive. The denominator is going to be negative, and we result in a negative number overall. Let me put these back in. So this first interval from -infinity to -2 is positive. This next one is negative. And the last one to test is 4 to infinity. So let's pick a number. Let's say it's 5. We plug in 5 into the numerator. Our numerator remains positive. Our denominator is also positive, so we have a positive. Okay, so the original inequality here asks us to find when it's greater than or equal to 0. Now remember that so basically we're looking at these two intervals, right? Because these are both positive. Now we want it to be equal to 0 as well. So from -infinity to -2, this time with a closed bracket, because if I plug -2 back into this expression, I do get 0, right? So that's going to have a closed bracket there. Union with the other interval from 4 to infinity. And now this time, notice that I am not putting a closed bracket here on the 4. Remember, if this polynomial, if x equals 4, then this is undefined, and we can't have that dividing by 0, so it's not technically part of our solution here. So we have 4 with an open bracket, but this would be our solution representing all possible x values for when this rational expression is greater than or equal to 0. Okay, now this next problem, these all get a little bit trickier now that we have multiple things on both sides. We don't have 0 on this side. Now your first reaction might be to multiply throughout by x minus 2 and x minus 1. The problem is, though, when we multiply by x minus 2 and x minus 1, we have no idea, is this a positive or is this a negative value? Because if it was negative, we'd have to flip that sign, right? So we can't actually ever, in an inequality, ever multiply by an expression containing our variable, because we don't know if that would be overall a positive or negative. So what we're going to have to do is actually move over this 1/6. Your goal is always, always to get 0 on one side. So you have to move over the 1/6 and then now solve this inequality and make it look more like what we have in problem number 5 here. Okay, so I'm going to go ahead and work on that. So key thing here is get 0 on one side, because you cannot multiply by a variable. Okay, so I'm going to work on combining all these fractions. So I'm going to multiply the first by 6 times x minus 1. So I have a big expression underneath. Okay, the middle term here, if I multiply this, I get x minus 2 times 6. I'm going to put that 6 out in front. And the last term is x minus 2 times x minus 1. It's greater than or equal to 0. Okay, so I'm just going to simplify the numerator here. So give me a second to do that. You guys can go ahead and simplify your numerators too. Okay, so I do want to make sure that you're not making any errors with your signs here. So a lot of times people will forget to like distribute that negative to the entire expression here, so just be really careful about that. But these are going to cancel, and I'm going to be left with negative x squared minus, or positive, plus 3x, 6, and negative 2, minus, or plus 4 here, and then over x minus 2 times x minus 1. Okay, now my goal again is to factor everything, so I want to find all my key numbers, so that means I need to factor this. Okay, so I'm going to pull that negative out, and I'm left with this quadratic here that I'm going to factor again. So I have opposite of x minus 4 times x plus 1 over 6 times x minus 2 times x minus 1. Okay, so this is getting pretty big, but now we have several key numbers, right? Our key numbers here are going to be positive 4, negative 1, positive 1, and 2. Okay, so it's wherever the polynomial we have a root, as well as wherever our denominator is equal to 0, because those are restrictions on our domain. So we have 4 different key numbers, and I'm going to now draw a number line and place all those values on this number line. So I have negative 1, then 1, then 2, then 4. Okay, so we've got 5 different intervals now to test. So negative infinity, negative 1, from negative 1 to 1, from 1 to 2, from 2 to 4, and from 4 to positive infinity. So let's write out our expression here. And we're going to test within this expression, this whole entire thing. I'm just going to rewrite that once so I don't have to write it every single time. And I'm going to test these underneath. So from, let's do negative infinity to 1, negative 1. Alright, so we're going to pick a number inside there. Let's try negative 2. Okay, so if we plug in negative 2, we still have this negative on the outside, so I'm going to bring this down. If I plug in negative 2 in here, x minus 4 is still negative. If I plug in negative 2 here into x plus 1, it's still negative. And then in the denominator, this 6 here doesn't really make a difference, so I'm going to leave that out. But this first polynomial, x minus 2, is going to be negative, and this second term, x minus 1, is also negative. So that results in, since I have 2 positives in the denominator, or 2 negatives in the denominator, 2 negatives in the numerator, overall I am left with just 1 negative. So this first interval is negative. Now let's test the next one from negative 1 to 1. Let's pick the number 0 and plug that in. Remember that that negative is still out in the front. So if I plug in 0, I still get 0, or sorry, negative 4, so it's a negative. If I plug in 0 here, I get a positive. If I plug in 0 here, I get a negative. If I plug in 0 here, also a negative. Overall, this polynomial, since I have these 2 negatives making a positive and these 2 negatives making a positive, overall everything ends up being positive in this interval. Okay, so go ahead and test the rest of those. I am going to show the work for it. I'm not going to talk it all through, and then we'll talk about how to write the solution. Okay, so here's the work for the rest of those intervals right here, and I'm just going to plug them back into here. So I have a negative, positive, and a negative here. Okay, now the original inequality here asked me for when it was greater than or equal to 0, right? After we rewrote that, so greater than or equal to 0. So we're looking for where our intervals will be positive, and that's within here, from negative 1 to 1 and from 2 to 4. So now let's talk about how to write this as a solution. Now, in our polynomial, x cannot equal 2, and x cannot equal 1, right? If that happens, then the denominator is 0. So I don't want to use those with open brackets, or sorry, with closed brackets. I want to keep those open. But from negative 1 to 1, with an open bracket here, and the union of that and 2 to 4 with a closed bracket, this represents all possible numbers for x in which our polynomial will be greater than or equal to 0. So that's my solution written out. sorry it's getting so messy. These problems do require a ton of work, and at least to be able to test and show where you're getting those values from. Alright, we've got one more problem here. Actually, I think this is the wrong problem. If you guys want to check the answer key, I did a different problem. I'm not sure why this problem is here. Hopefully it's not like that on your packet too. I'm going to change the problem real quick. Okay, so this is the problem that I want you guys to do. Make sure you subtract 1 over first before you begin this problem. So rewrite this as this, and then try to combine these fractions here to make one large polynomial, and find your key numbers, test those regions, check your answer with the key, and we'll talk more about this tomorrow and clear up any questions or concerns you guys have on this section. So I think that's it. 25 minutes is pretty long. Thanks for sticking in there. Good job.